So I'm Roger from Nous Research. We train open source language models. Today we're going to be talking about some of our RL infrastructure. So I'll first give a motivation for like reinforcement learning in general, or like how I like to think about reinforcement learning. And I'll talk about a little bit about like the RL infrastructure at Nous, and specifically I'll focus on our environment abstraction. So start with like supervised learning. Yeah, you guys kind of like know the deal. You have some model, you have some data set, some loss function, and you want to like take some steps on your model. You want to make small updates to your model to optimize that loss. So it kind of like looks like this, right? Like you have some like kind of like nice loss function, well behaved, like smooth, continuous, and like a step of training and supervised learning kind of looks like you take this like this ball, and you press play on this picture and you kind of like pause it, and the ball moves over like a little bit, and then that's like one step of training. But like, does this work for like any arbitrary like loss function you can write down? And the answer is like no. Like consider accuracy, right? It takes on n plus one like discrete values if you have like data set of size n, like 0 over n to like dot dot dot, like n over n, right? What would like the same plot look like if we use like accuracy instead? I guess like error rate or something, if we want to make it like a visualization problem. So that's going to look like a piecewise constant function of like any weight that you pick from your model, right? So the ball doesn't roll anymore. So that's like one limitation of supervised learning. Like where does this like sort of show up? Well, like if you're doing language modeling, every time you're picking a token, like you can't backprop through that picking operation anymore because like the next token would be like kind of like the index of the chosen token is like a piecewise constant function, like any weight. So you introduce like this piecewise constant node into your compute graph at that point, and then like that means you can't really backprop through like multiple picking operations for these tokens. So what that means is like under like greedy sampling, supervised learning can't really help you with objectives on multiple tokens. If you're interested in like rewarding a language model for like how funny like a joke is or something, you can't like directly approach that with supervised learning. Okay, so these are some limitations of supervised learning. It only works with like nice loss functions, right? It doesn't play well with objectives over like multi-step trajectories that don't decompose well into like these single-step objectives. The main medium that the modeler has to communicate with the model is data. So we need like expert samples of what is good. And there's like a kind of deficit, which is like there's no way to demonstrate what is bad in supervised learning. You kind of you have to tell the model very well like what is good. There are like kind of surprising results, like weak to strong generalization. But like in general, like the model outperforming the expert labelers would be like kind of very surprising. Okay, so moving on to RL. In RL, we have this like different setup where we have this like agent in an environment, and it can take actions and influence the environment, and then get rewards. And the rewards can sort of like be anything. They're like up to us, and they're usually kind of like weird, really behave functions. Like they can be discrete, they can be like points in a game, they can be like the accuracy. That's totally fine in RL and normal. And the goal is to learn this like policy which controls this agent to maximize the sum of like discounted rewards over time. So like going back to the language modeling world, like how does like RL directly map onto language modeling, or like language modeling map onto RL? So the states are like the text prefixes. So the initial states like the prompt, the actions are the next tokens. That means like a language model is like exactly what a policy is, right? A policy maps the state to a probability distribution over next actions. A language model maps the text prefix to a probability distribution over next tokens. So all we have to do really is like specify our favorite reward function, like how funny like our joke is, whatever. And then we can optimize our model against this with like all of the fancy algorithms from RL. So this is just like some write-up of like the RL objective. And it kind of shows like, the trick here is like there's this expectation, right? You're taking an expectation over the policy. And so the thing on the inside, that thing might be like discrete. That's like reward, whatever. Like you might have some like accuracy thing as your reward. But we're kind of like, we kind of like describe the reward using this like high level language of like how humans might assign rewards. But then we're kind of like compiling this back into like a differentiable loss function with this expectation thing that like smooths things out. So that's like kind of the trick here. So in that sense, like rewards are sort of this like abstraction. Like we end up with a smooth like differentiable loss at the end, but like we have this like language of rewards to communicate intent to the model. And like you can like do some math to like optimize the model, policy gradient. Okay, so the like the math that's or the algorithm that's implied by like policy gradient is sort of like reinforced, where you can like take rollouts, you can take samples from your model, and kind of like estimate this this gradient in policy gradient with the mean of these returns from the rollouts. This is like a quite a simple algorithm. If you kind of like if you kind of stare at like this part, it sort of looks like just like weighted supervised fine tuning, right? Like you have this like log of like the probability of a token and then like some like weight on it. And reinforced, this is like the return, but it doesn't have to be that. Like you can replace it with like some advantage. Like GRPO does that, right? It's like the reward norm, the mean, like the normalized rewards. This like this is kind of like nice, right? So in RL, like we can work with like nearly arbitrary rewards. So discrete, non-differentiable, whatever. You can have objectives over these like multi-step trajectories. You can communicate intent to the model like in this like additional way, and you can also demonstrate like what is bad in addition to like what is good simply through like negative rewards. The model outperforming expert labelers is possible. The model learning like self-correction is like expected, yeah, we've seen like kind of cool emergent behaviors of like like O1, O3, R1 kind of these like thinking models that kind of learn their own approach to solving problems. Okay. So we're now like kind of moving into this era of experience. So like since 2020 or so, like maybe even before that, we've been scaling up data, pre-training data, SFT. The goal being to get this like very diverse, large pool of good inputs, high quality inputs to train our model. And now like we're kind of motivated to do the same thing for RL environments. And like previously, I guess like the format of the data wasn't so important because like there were these like shared GPT or OpenAI format or whatever, and it was kind of annoying that there was like multiple formats, but it was kind of easy to interconvert between them. But these environments are sort of like written in code, and it's like much harder to kind of like share these environments. So in open source, we kind of like want to build up our collection of like, just like how we built up this like huge pool of like data, we want to build up this like huge pool of environments. And so like there just needs to be some kind of like standard for open source developers to all like work together to like build up this, to scale environments up to like millions and millions of environments. So we want to pose a question here, like what is the abstraction that will allow open source to scale up to 1 million environments? What would that look like? Okay, so I guess like first like we can think about like where the environments like live in the larger picture of like some training infrastructure. So at Nous we have this like distributed training like infrastructure. It's pretty standard. We've got these like 3 microservices. So the trainer is one microservice, handles like backprop. Inference is another microservice, right? It's like an OpenAI API that serves the model, the current policy. And we also have this like environment manager / like rollout service, which handles all of the environments. And each of these environments, if you have like multiple of them, is also its like own microservice. So that means that each environment can have its own like kind of code execution environment, or like Python environment, or like it can run on its own hardware. If for some reason you want to like run an environment like on your phone or something, like you could just do that. And these environments run like async from the trainer, right? So they don't like really care about the trainer. They're just like, their goal is just like constantly produce rollouts, constantly produce like data and never stop. If you wanted to like resurrect some kind of ancient environment from like 2019, you can just like make like a Docker container or something, and you can run like this like ancient environment. Okay, and the environment interface, like I guess the minimal environment interface that we kind of expose is rather simple. So it's just like these like 2 things. There's like a lot of other stuff that you can do, like like logging and whatever. But like at a minimum, like these 2 things. So get item and collect trajectories. So get item is like kind of like just a data loader kind of like a function. So you can get like a row from your data set, or if you like are working with like larger batches, you can kind of get a batch from your data set. If you have like some fancy curriculum you want to do, getItem kind of can manage that curriculum for you. And then collect trajectories takes in any kind of item that's returned by getItem, and then maps it to a group of scored rollouts. I guess it's kind of like good that we okay. So I'll try to like motivate why we have this like collect trajectories function. So like I guess another like common kind of abstraction is like we split up the rollout part from the scoring part, or the inference part from the scoring part. But collect trajectories is a fusion of both of these. It handles both inference and scoring, and we deliberately chose that because like what happens when you try to like do like multi-turn or like multi-agent with like a separate scorer function? Then things kind of get like weird. So we have this like fused inference and scoring function, collect trajectories, where we're kind of agnostic to how many times like inference and scoring happen. Multi-step, multi-agent are kind of like automatically supported by this method. Okay, and the atomic unit of training data that's produced by this function is a group. So this kind of encapsulates like what the data preparation would look like for like DPO, GRPO, SFT with like group size 1. It also allows you to customize like what a group even means, right? So GRPO is like has a setup where like a group is like you have like multiple rollouts for the same problem, but it doesn't like kind of have to be that way. If you wanted to like, for example, sample a batch of like similar problems, for example, I have this example here of like same like chess position, but it's just like black to move in one and white to move in the other. On the left, it's like mate in 1 for black. On the right, it's like mate in 18 for white. Right. So if you want to like group like similar problems together instead of like having the same problem and like doing multiple rollouts, like you can totally do that with this. So we don't lock you into like the GRPO official like definition of what a group is. Another like kind of weird quirky thing about our design is that at least for text, the thing that's returned by each of these environments is like the literal tokens. So it's not text, it's not like messages, it's the tokens. This allows you to deal with like weird little quirks about like inference. Like for example, like maybe your inference API gives you like an EOS token even if like your max context length is like exceeded. So it inserts this like kind of fake EOS. The model didn't want to stop, but it was like forced to stop. So you kind of like want to strip that out when you're training on it, so the model doesn't like stop in the middle of its like generation. Say you wanted to like make a waifu group chat environment or something, right? So you have like the roles being like the usernames or something, right? And that requires a custom chat template, and that's totally fine. We can support a per environment chat template in this framework. Another thing you can do like in like the token world is like the trainer is now like agnostic to like chat versus instruct model. And what that means is like you can do all of like the cool like R10 kind of style like experiments. But it also means that you can mix together instruct and base model fine tuning like all at once, right? So for example, you can do like if we're training this like code assistant model, or you can do chat code assistant style RL. But you can also mix that with like base model style like auto completion RL. And another thing you can do if you have like the environment return tokens is you can override the GRPO advantages. So the GRPO advantages are like just like kind of token level weights on the SFT, right? If you had some reason to like some way to like kind of get token level rewards, for example, you have like some stack trace from your like interpreter, and you see like exactly which lines are like involved in the error. These environments can then override the advantages like computed by the trainer, and you can have like token level rewards or like weird like token level like reweighings of the advantages. Okay, we wanted to make this kind of like extensible. So this is just an example of like some kind of like extension that I thought of. Like suppose that you wanted different environments to support different like attention masking schemes. So like if you had like super long context for some environment, maybe you would want to use like sliding window attention for that one. If you had some kind of like smarter way to do like sliding window, if you maybe just like if you had some like protein question answer environment where you put in the protein sequence and you like try to ask the question about it, maybe you want to only do attention where like the contact points of the tertiary structure are. So like maybe you want to do something where you like your environment passes the inputs to like a flux attention block mask getter within this like score data group that's returned. Okay. So these environments are kind of like extensible. You can come up with your own like weird wacky things that you want to like give the trainer. Okay. So all of this was like joint work with Dakota, Shannon, Jay Chen, and Technium, and thanks to Alessio and Swix for hosting.